Hi everybody, and welcome to our module on positive and negative predictive value. In the module on sensitivity and specificity, I talked about diagnostic tests and choosing cut points for which patients would be declared positive or negative. In this module, we're going to talk about something different. So what doctors and patients want to know from a diagnostic test is, I have a positive result, what's the likelihood that I have disease? Or conversely, I have a negative result, what's the likelihood that I don't have disease? And it's very important for you to understand that sensitivity and specificity do not answer these questions. For these questions, which are the highly relevant clinical questions, we need to know something called the positive predictive value and the negative predictive value. So let's revisit the 2 by 2 table, which I described in detail in the module on sensitivity and specificity. But this time we're going to use the 2 by 2 table to calculate something called the positive predictive value. So just like the name implies, the positive predictive value is the percent of positive results that are accurate. So in order to calculate this, we want to take the true positives, the patients who truly have disease and are identified as positive by our test, and divide by all the positive results, which are the true positives plus the false positives. And if you have trouble remembering this equation, just remember that the positive predictive value is the top row. The trues always go on top, so true positive is on top, and the total number of patients in the top row go on the bottom. That's the true positives plus the false positives. The negative predictive value, on the other hand, is just like its name implies. It's the percent of negative test results that are true negatives. So the true negatives go on top, and all the negative test results go on the bottom. And it's easy to remember this because it's just the bottom row. You always put the trues on top. That's my little rule of thumb to help you out. And then you divide by the sum of the two numbers in the bottom row, and that's how you get the negative predictive value. So here's a sample of the type of question you could be asked about this. A test has a sensitivity of 80% and a specificity of 50%. The test is used in a population where disease prevalence is 40%. What is the positive predictive value? So the first thing you always want to do in questions like this where you're given prevalence is create 100 imaginary patients and divide them up by the disease prevalence. So the disease prevalence is 40%. So we're going to put 40% of these 100 patients, or 40 patients, right here, and that represents the sum of all the patients in this column, all the disease positive patients. The other 60 patients we're going to put right here, and that represents the sum of all the patients in this column, the disease negative patients. Now, to decide how we're going to split up these 40 disease positive patients between positive and negative test results, we're going to use the sensitivity. The sensitivity is 80%, so we're going to put 80% of the 40 patients in the top quadrant, that's right here, and then we're going to put the other 20% right here. For the 60 disease negative patients, we're going to split them up based on the specificity. So the specificity is 50%. So we're going to put 50% of the patients, or 30 patients, right here, and put the remaining 30 right here. So now we have filled in this entire 2 by 2 table using sensitivity, specificity, and disease prevalence. And that's a very important skill for you to have before you take step one. Make sure you know how to do that. Once we have all the numbers filled in, we can go ahead and calculate the positive predictive value just using that equation. And remember, the positive predictive value is everything in the top row with the trues on top. So the true positives go on top, that's 32, divided by the true positives plus the false positives, which adds up to 62, and that gives us a positive predictive value of 52%. Now I'm going to talk about a very important and high yield point, and that is the fact that unlike sensitivity and specificity, positive predictive value and negative predictive value are highly dependent on the prevalence of disease. So in order to understand this, we're going to work through an example, and this is the exact same example I used in the sensitivity specificity module. In that module, I used a test in two different groups, one where disease was highly prevalent and one where it was not highly prevalent. And I showed you that the sensitivity and specificity did not change. They are the same no matter the prevalence of disease. We're going to repeat that calculation now for positive and negative predictive value. So let's suppose test X has a sensitivity of 80% and a specificity of 50%. And we're first going to test it in group 1 where disease prevalence is 80%. So we're going to create 100 imaginary patients here, and we're going to split them up by disease prevalence. So 80 of them go over here for disease positive and 20 go over here for disease negative. Next, we take those 80 disease positive patients and we split them up based on the sensitivity. So 80% of them go up here, that's 64, and I get that number from the sensitivity of 80%. 80% of 80 is 64. The remainder go down here, that's 16. For the 20 disease negative patients, I split them up 50-50 because the specificity is 50%. So I put 50% of them here and I put the remainder here. Now we have all the numbers in our 2 by 2 table to go ahead and calculate the positive predictive value. So positive predictive value is the top row, and the trues go on top, so 64 true positives on top, divided by the total number of patients in the top row, which is 74 on the bottom, and that works out to 86%. So the positive predictive value in group 1, where prevalence is 80%, is 86%. Now let's repeat that calculation for group 2, where prevalence is 20%. So once again, we're going to create our 100 imaginary patients. We're going to split them up by disease prevalence so that 20 of them are here and 80 of them are here. For these 20 patients who have disease, I'm going to split them up based on the sensitivity and put 80% of them here, that's 16, and the remainder go here. For the 80 disease negative patients, I'm going to split them up by the specificity, so 50% go here and the remainder go here. Now we have all the numbers filled in our 2 by 2 table, so we go ahead and calculate the positive predictive value. That's the top row. Trues are on top, so 16 on top divided by 56 on the bottom, and it's 29%. So what we've done is shown that the positive predictive value falls from 86% to 29% when disease prevalence falls from 80% to 20%. And I went through this calculation to illustrate for you that the positive predictive value is highly dependent on the disease prevalence. And this is very different from sensitivity and specificity, which do not change based on disease prevalence. Here's another example of the negative predictive value tested in 2 populations. So I won't go through all the math. You can do that on your own if you wish. But for group 1, where the prevalence is 80%, we get a negative predictive value of 38%. For group 2, where the prevalence is lower, we get a negative predictive value of 91%. So the negative predictive value increases when we move to a population where disease prevalence is lower. So a key point here is that the positive predictive value is higher when prevalence is higher, and the negative predictive value is high when prevalence is low. And you can memorize this if you wish, but it's very logical if you think about it. Let's assume that we have a 20-year-old marathon runner who has an abnormal EKG. The prevalence of coronary disease among 20-year-old marathon runners is very, very low. It's a low prevalence. That means the positive predictive value of your EKG is going to be very low. It's highly likely that that EKG is in error and it doesn't represent true coronary disease. And this is actually a fact you need to know when you're taking care of patients. On the other hand, imagine an abnormal EKG in an 80-year-old smoker who's had prior bypass surgery and has diabetes. The prevalence of coronary disease in that type of patient is very, very high. So it's highly likely that that abnormal EKG is correct. The positive predictive value in that very sick population with a lot of coronary disease is very high. So these are just examples to illustrate for you these facts that I've listed right here, which is you have to think about the population you're using your test in when you think about the implications of a positive or negative result. Now let's talk about what happens to the positive and negative predictive values when we move the cutoff point of a diagnostic test. So in the module on sensitivity and specificity, I talked about what would happen if we sampled the blood glucose level in a group of normal patients represented by this blue line here, and a bunch of diabetics represented by this red line here. And then we plotted the blood glucose level along the x-axis and the number of subjects with each test result along the y-axis. We would get 2 curves, one blue, one red for the normal and diabetics, and there would be some overlap so that wherever we chose as a cutoff for the test, we would identify a mixture of true and false positives and true and false negatives. Well, if we talk about a test result that has a cutoff right here on this dotted line, what you need to know is that moving it to the left lowers the positive predictive value. To understand this, let's go through a little bit of math. So recall that the positive predictive value is true positives divided by true positives plus false positives. And let's suppose we start at point A right here. Well, the true positives are going to be all the patients under this red diabetic curve here. These people have diabetes and they're positive by our test because they're above the cut point. So that's going to be our number of true positives. But we also have some false positives because all these patients under the blue curve here are normal, but our test is identifying them as positive or abnormal. So we're going to have a small number of false positives. Now let's suppose we move the cutoff to point B. Well, what happens now is we're going to increase our number of true positives because almost everyone under this red curve of diabetics is going to be classified as positive. They will be above the cut point. So we will increase our number of true positives. And that might make you think that the positive predictive value is going to go up, but it doesn't. And the reason is because although our true positive rate has gone up, we've also increased our false positive rate. all these people under the blue curve that I'm marking with my pen right now will be falsely classified as disease positive because they will be positive by our test because they are above the cutoff point. If this doesn't totally make sense to you, I've done a little hypothetical math up here. So let's suppose we have cutoff point A. We have 10 true positives, and those are all these diabetics under the red curve right here, and 5 false positives, which are these small number of normal patients who are above the cutoff point. That gives us a positive predictive value of 10 over 15 or 66%. Now let's suppose we move to cutoff B. Well, now we've got true positives that have gone up to 15. They were 10 before, but now they've gone up to 15. All these diabetics here are classified as true positives, but we've also increased our false positives from 5 over here to 10 over here, because now all these normal subjects are above the cutoff point and they're classified as false positives. If we do that math, the positive predictive value is 15 over 25, and that works out to 60%. So you can see that we have lowered the positive predictive value by moving the cutoff this way on the curve. Now, to be completely honest with you, all that math is kind of confusing. So if you want to make it simple for yourself, just remember that moving the cutoff this way lowers the positive predictive value. And then you can figure everything out from doing opposites of this. So if moving the cutoff this way lowers the positive predictive value, then moving it that way must raise the positive predictive value. And then negative predictive value is the opposite of positive predictive value. So you can figure everything else out by just thinking it does the opposite of what positive predictive value does. So for example, moving the cutoff this way will increase the negative predictive value, and moving the cutoff this way will lower the negative predictive value. That's the opposite of what positive predictive value does. And you can remember all this by just remembering this one point that I'm circling right here. So let's suppose that the American Diabetes Association proposes lowering the cutoff value for the fasting glucose level that indicates diabetes. How will this change affect sensitivity, specificity, positive predictive value, and negative predictive value? Well, now we've gone over all these things between the module on sensitivity, specificity, and this module. So we talked about how moving the cutoff this way, lowering the cutoff, increases the sensitivity of a test and decreases the specificity. And then we just talked about in this module how moving the cutoff point this way on the curve will decrease the positive predictive value, and then negative predictive value will always follow the opposite rule, so it will increase. So now you know how to answer questions about what happens to moving the cutoff point on all 4 of these features of a diagnostic test. And that concludes our module on positive and negative predictive value.